Hello everybody, this is Professor Iris Miano giving you Day 19 lecture concerning sections 6.4 and 6.5, trig identities for 6.4, and then the sum and difference identities in 6.5. So there's not really anything new to present in 6.4 section. All of these identities have already been presented to you, and I mean there's just this definition of being identically equal that's relatively new. Nothing too earth-shattering happening there, though. It's just saying that one function is equal to another as long as all of their outputs are equal, and inputs are equal too. And then this just is the formal way in which we establish an identity. And so yes, what else can we say about this? Well, here again are your quotient identities, your reciprocal identities for the trig functions, Pythagorean identities based on the most fundamental one of sine squared theta plus cosine squared theta equaling 1, and then the other two are subsequent manipulations, even odd identities. Yeah, so nothing new there. This blue box is giving us guidelines for establishing identities, which is that we almost always want to start with the side containing the more complicated expression, and to turn it into the less complicated version of it. We're going to rewrite sums and differences of quotients as a single quotient. Sometimes we'll help to rewrite one side in terms of sine and cosine functions only. Keep in mind as you manipulate one side of the expression that keep in mind the form of the expression on the other side. Sure. So we'll want to take into account all of these things while we establish these identities. And I didn't see in the textbook that they did this particular kind of structure, but this is the way that I was taught when I first tackled these items, which is to say, okay, let's look at this first identity where we have secant theta times sine theta equaling tangent theta. So according to the guidelines, we want to work on manipulating the left-hand side of the equation, and usually the more complicated stuff is on the left-hand side. So what I would do when I was in this position, and I'm going to go ahead and actually, for this part, I want to do it in black. I'm going to draw a horizontal line and then a vertical line at the equal sign, which is to say that the tangent theta goes over here, and whatever manipulation I'm going to do on the secant theta times sine theta, it's going to be on this left-hand side right here. Okay, so the secant theta I'm going to rewrite as 1 over cosine theta. And it's going to be multiplied by the sine theta. Okay, you can probably see already how this can easily turn into a tangent theta, right? Because I can just put that sine theta over a 1, perform the multiplications, voila, it's sine, oops, excuse me, let me just get rid of that real quick. It's sine theta over cosine theta, performing the multiplication of those fractions, so to speak, right? Sorry, I just want to move that cursor away. It's bothering me. And I want to now formally define this as tangent theta. And then once the tangent theta, or sorry, once the left-hand side matches the right-hand side, I usually just repeat writing what the right-hand side is. It just kind of drops down, so to speak. Okay, and then my identity is established. I have the same thing on both sides of the chart, and we're good. You do not have to follow this chart mechanism that I'm demonstrating to you. This is just the way that I like to do it, okay? Cool. So here's another identity that we need to establish. Sine u, a cosecant u minus cosine squared u is supposed to equal sine squared u. But how? Let's do this thing. All right, so I'm going to draw my horizontal line, a vertical line. I'm going to rewrite my cosecant u as 1 over the sine u, and we'll see that something fun gets to happen there. So let's call it sine u times 1 over sine u minus the cosine squared u. And you'll notice what's happening here right away, since that sine u can be put over 1, those bits right there can slash away, right? And we'll just be left with a 1 for this first term. So that's going to be 1 minus cosine squared u. Now that's not looking like sine squared u yet, but wait, if we go back to the Pythagorean identities, we can use slight modifications of these guys. So by that, I mean, you can redefine the cosine squared theta as 1 minus sine squared theta. If you just subtract sine squared theta from both sides, you will get that, equivalent equation. So that's what I'm going to use right here. I'm going to say, hey, I know that 1 minus cosine squared u, according to the Pythagorean identity, a slight modification of it is equal to sine squared u. And now I have it matching what I had on the other side. Cool, identity established right there. Moving on. Here's another one. And what do we do? Okay, well, if you're following along with me, you're going to do this as your first move. And we're going to, what are we going to do here? We're going to use that same modification of the, what's it called? Pythagorean identity. In fact, we're going to use it here and here because 1 plus cotangent squared theta, if you look back on its corresponding Pythagorean identity, plus cotangent theta, it can be, outrightedly replaced by the cosecant squared theta. So we're going to do both of those substitutions at the same time, if that's okay with everybody. So again, 1 minus cosine squared theta can be rewritten as sine squared theta. And then 1 plus cotangent squared theta is cosecant squared theta. Well, the cosecant squared theta is actually 1 over the sine squared theta. And then check this out. Put this over a 1. And then slashy slash, boom, boom, and you are just left with a 1. Fun, right? It can be. Oops, I didn't need to turn that back to black. I have my own black marker here. So that's just a big fat 1, which is what we had on the left-hand side. So the identity has been established there. Bing, bang, boom. Some of these can be quite fast. Okay, where am I putting? Oh, I just put them in the back, I guess. Oops. I haven't put them anywhere because that was just my first page of my notes. Okay, sorry for thinking out loud there. Don't mean to distract you guys from what's being presented here. Okay, next we have this guy. In fact, just to give myself more room, I'm going to go ahead and put this over here for this one. Now, how will I choose to modify the left-hand side to begin with here? Now, just to be clear, I meant to have this be the equal sign. It's supposed to line up with this vertical line, or that's my intention in any event. So I'm going to go ahead and choose to rewrite sine squared theta here on the left-hand side by a 1 minus cosine squared theta. And then I'm going to do some fun, clever factoring. Okay, so here we go. Instead of sine squared theta, it's going to become a 1 minus cosine squared theta in the numerator. And that's going to be below a, or followed below by a cosine theta, 1 minus cosine theta, that is. And then I'm going to factor this guy right here. Okay. Difference of squares, factorization, because 1 can be thought of as 1 squared, right? Okay. Difference of squares. Remember that old chestnut? All right, so that'll become 1 minus, this will be 1 plus cosine theta, 1 minus cosine theta. That's supposed to be a plus. So this 1 minus cosine theta bit will go ahead and cancel out. Right, so we'll think of this as a binomial factor in the denominator that matches up with this one, slash slash. Oh, I usually slash these things in red here. Let me be consistent with that, actually, because that's just more fun. Slash and slash, and then put it back to blue, but then also take my black marker and say, all right, now I have 1 minus 1 plus cosine theta. We've got to distribute through this negative sign here and there. So we'll have 1 minus 1 minus cosine theta. 1 minus 1, well, those are opposites. And they will cancel each other out, and we'll just be left with this here, which is negative cosine theta, which is exactly what we were meant to establish. Fun. So there you have it for that one. All right, cool. Now they just get more complicated as we go. So this one I have a fair amount of space dedicated to this, and so I'm going to draw a horizontal line and I'm going to split it kind of roughly in half. Have the equal sign that meant to be lined up with that vertical line. Okay, so looking at the left-hand side here, it looks quite complicated, and I have two rational expressions that I would like to add them together. So let's go ahead and establish an LCD. What is the LCD here? So I'll go ahead and just put it off to the side. Above the LCD looks like it's a 1 plus sine V times cosine V. If I want to add these two rational expressions together, just multiply together their denominators to get the LCD, because their denominators do not share any common factors. Okay, so in doing so, I will get the following. So stay with me, it's going to get kind of messy. Cosine V over cosine V. And I'll put them in parentheses just to, make everything nice and safe. It's going to be multiplied by cosine V over 1 plus sine V, and that's plus 1 plus sine V over cosine V, but multiplied by this fun one that's going to get me that common denominator of 1 plus sine V over 1 plus sine V. Okay, yes. So what do I hope to accomplish with this? Well, I'm going to multiply out this binomial business over the same denominator of cosine V, comma, 1 plus sine V, right? So we could put more things in parentheses if we really want to. So in any event, this is what it'll look like once I multiply these out too. So it's like I'm squaring a binomial factor of 1 plus sine V. So I'll have cosine squared V plus 1 plus 2 sine V's, sine V plus sine V squared, sine squared V rather. And then that's all over my cosine V 1 plus sine V. Okay, so very much cleverly, you may notice that you have a cosine squared V plus sine squared V. And what is that? Well, that's just a 1. This is a factor of 1 right here, according to the Pythagorean theorem, or Pythagorean identity rather. So then this becomes 1 plus 1 plus 2 sine V all over cosine V times 1 plus sine V. Okay, so we can add these together and we will get what? 2 plus 2 sine V. Nothing too spectacular yet, but wait, there's a GCF in the numerator that we can factor out. And we should, because watch what's going to be left over. 1 plus sine V. Ooh, cute, because there's a factor of 1 plus sine V that I would love to get rid of. If you guys have lost sight of what we were trying to do here, let's look back again at what was supposed to be, the thing that we're going towards, a factor of 2 with a secant V, which is a 1 over cosine V. So as you can see, I'm heading right towards that in just a moment. Let me go ahead and recognize that we're going to slash away a factor of 1 plus sine v, and then that'll give me a, almost there, guys. I'm going to have to go off to the side here because I kind of ran out of room here. 2 over cosine v, which is 2 times secant v, which is what I was trying to establish earlier. 2 secant v. Yay! Identity established. So much fun. Oh my gosh, I love these so much. Such a good time. But only when they make sense. So that's totally the purpose of me demonstrating just a bunch of examples here. Is just, I want to try and get it to make sense for everybody. Okay, so we're going to try and turn this rigmarole, this rational expression with a bunch of sine squareds, cosine squareds, tangent, cotangent, into just simply a tangent squared theta. And here we go. All right. So the first thing that I want to do is I want to rewrite tangent and cotangent in terms of sine and cosine. Okay, so that's going to be my first move. So again, we're just focusing on the left-hand side here. So that'll be sine squared theta minus sine theta over cosine theta over cosine squared theta minus cosine theta over sine theta. Okay, and then the thing that I decided to do was to make common denominators happen, right? So I'm going to multiply a fun one of cosine over cosine here, so that'll look like this, cosine theta over cosine theta in the numerator. So to multiply this one by it, and then this will get a factor of sine theta over sine theta. Why? So I can make these subtractions happen in the supernumerator and superdenominator all one thing. Okay, so here's what that'll look like in the next step. It'll be sine squared theta cosine theta minus sine theta all over a cosine theta. And that's just what I'm calling the supernumerator. And then the superdenominator, it's going to be cosine squared theta sine theta minus sine theta. Oops, that's supposed to be a theta over sine theta. Oops, cosine theta is supposed to be right here. Let me erase that quick. Quick edit there. That's supposed to be cosine theta in this position, and that's all over a sine theta. Okay, and then I did some keep, flip, change, and clever factoring. Okay, so I kept this guy up here. I'm dividing by this rational expression, so I'm going to change it to multiplication and flip this one over. So stay with me, folks. It's going to be, oh, and also for each of these numerator bits, which this one's about to become the denominator, I factored out the common either sine theta or cosine theta. So that's sine theta times sine theta cosine theta minus 1 over cosine theta. And so this is just me keeping the supernumerator rational expression while factoring out a sine theta. And now I'm going to change the operation from this long division bar. This main division bar is going to now become multiplication, and then I'm going to flip over this guy. So that sine theta is now going to be in the numerator, and the new denominator is going to have a cosine theta factored out of it. Cosine theta sine theta minus 1. Okay, and then check this out. Stuff's going to cancel, believe it or not. Okay, so this cosine sine, right, even though they're in different positions down here, it doesn't matter. It's still the same value in the first term position, and then we're subtracting off a 1. So technically they're the same and get slashed away. And then we're left with what? Check this out. That's sine theta over cosine theta times sine theta over cosine theta, which is tangent theta times tangent theta, which is tangent theta squared, which is what we wanted. I'm a really bad judge of how much room I need, and I'm wasting all of this space over here to establish this chart-like, format that I'm used to. It's I don't know, in my mind, establishing an identity is you work on one side and you get it to match the other side. So the other side of the workspace is meant to be left blank in that regard. I don't know if that's necessarily a good strategy or use of space at all. It clearly isn't a good use of space, but it's just along the lines of the way that I was always taught, so that's the way I like to do it. Okay, sorry if that's weird for you guys, and if you don't like it, don't do it. Don't even worry about it. My feelings won't be hurt at all. Okay, so here's the last identity in this section that I wanted to establish. This one's more, bizarre one. And I definitely want to give myself a healthy amount of space here. Here's the division, or the equality bar. And this one's definitely the most complicated one that I saw in the homework set. So where do we want to start with this? Well, notice that we have some complicated stuff being squared. I think it would behoove us to just kind of square all of that stuff out. I'm going to not, though, distribute through the a squared in the second term. I'm just going to leave it where it is, at least for a moment, okay? Because it's going to be factored out of the entire expression in a later step. Not that you would necessarily know that ahead of time. So go ahead and, with me, square out this exponential and square out this this binomial as well, and see what do we get. We will get 4 a squared sine squared theta cosine squared theta. Oops. Let's change the position of that for the first term, and then plus, remember, let that a squared come along for the ride, and just let it hang out in front, and let's square this binomial. So that'll give you cosine to the 4th power, I know, kind of crazy, theta, minus 2 times sine squared theta cosine squared theta, plus sine to the 4th power theta. Okay, then we will want to factor out the a squared from both of these, okay? Trust me, it's going to work out beautifully. So then that'll be able to free up the parentheses here, and then all of the remaining terms will be able to linger with one another, like intermix. So that'll leave us with 4 sine squared theta cosine squared theta plus cosine to the 4th power theta minus 2 sine squared theta cosine squared theta plus sine to the 4th power theta. So as you can see, we have a couple of like terms here, and I want to change the color on that. Yep, this bit and this bit can be combined. So we'll have 2 sine squared cosine squared thetas left after that. And so that'll be looking like this. Cosine to the 4th power theta plus 2 sine squared theta cosine squared theta plus sine 4th power theta. So if you know your perfect square trinomials here, you will recognize that this can be factored into a perfect square trinomial of, check this out, cosine squared theta plus sine squared theta squared. But what's the value of this thing inside? Well, hold on, let me actually, I want to use this blue. The value of this inside, according to the Pythagorean identity, is a 1. And a 1 squared, right, is still just 1. So that's how this ultimately establishes as just being valued at a squared, which is what we wanted, right? Back at the beginning here. The identity we wanted to establish was just an a squared, and we did it. Oh, we had a little bit of room to spare on this one. Lucky us. Okay, so now that's all that I have to say about 6.4. I'd be delighted to do more examples, weirder ones, different ones than what you've seen. Just let me know. Okay, so we're going to get now into the sum difference formulas. So these are new for you, and you may have seen these sum difference for the cosine and the sine and the tangent before, and you might have already established some chants or songs associated with them. And I've scoured the YouTube videos to see like what's already been put out there, because I don't really have one, to be honest. Like, I've heard of other people having songs that were presented to them, and I mean, you know, I've heard some along the way, but I never really had a lot of them that stuck with me personally. I've had memories of sine, cosine, cosine, sine, cosine, cosine, sine, sine kind of thing. So if that's something that speaks to your heart, you already know, then awesome, great. There's this other identity that we want to establish as well, which is just saying that the cosine is just a shifting of the sign and vice versa. So we already kind of dipped into that a little bit with the phase shift that was presented. But anyways, here, among the videos that I looked at, as far as a fun song and dance, a lot of them were just terrible and had all of this preamble of like, oh, my teacher taught me this song, and like going into like the philosophy of why we would want to learn a song, and I was just like, oh my god, just get to the point. But here I found a video that I thought was really cute and simple and quick. It was just for the sums, but you can come up with a similar thing for the differences as well. So I'm just going to go ahead and click on it and have the link take us there.
Sine, cosine, cosine, sine, cosine, cosine, sine, 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 tangent, tangent over 1, flip the sign, tan, tan, done.
Wasn't that cute? And she bows at the end. Oh my god. So I don't know who Christelle Vincent is, but I love her so much. Let's watch that one more time together. And also, when she says sine, sine, sine here, that is to indicate that for the cosine sum, you change the sign from addition to subtraction in the formula. Okay? So keep that in mind when she sings it this second go around. Okay? Here we go.
Sine, cosine, cosine, sine, cosine, cosine, sine, 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 tangent, tangent over 1, flip the sign, tan, tan, done.
Oh my god, adorable. Just love her. Okay, so that's the one that I found that I thought was the least annoying, but by all means, like, come up with whatever it works best for you in order to memorize. Yes, unfortunately, I said memorize these formulas because you're gonna need them. All right, now let's get into a series of examples, and this is where the bulk of the lecture is going to be had, where I'm going to just show you a bunch of examples of various types of exercises where you use these formulas, and yeah, and I'll just give you some pointers along the way as much as I possibly can. Okay, so let's start with finding the exact value of the sine of 105 degrees. And again, we are meant to do this without a calculator. We're going to split this 105 degrees either into a sum or a difference of degree measures for angles that we know very well their sine. Okay, so I, thought about this for a second, and I said to myself, okay, well, this lends itself very well to being the sine of 45 degrees plus 60 degrees. Okay, now if that's not something that's like terribly intuitive, would have taken you a few minutes to come up with that, no problem, okay? So, in any event, let's use the sum formula for sine, which is sine, cosine, cosine, sine, right? And we keep the sign of addition in between them. So that's the sine of 45 degrees times the sine, or the cosine of 60 degrees, excuse me, plus cosine 45 degrees sine 60 degrees. And we'll replace, right? And go back to your unit circle if you haven't memorized these yet. The sine of 45 degrees is root 2 over 2. The cosine of 60 degrees is 1/2, plus the cosine of 45 degrees is root 2 over 2. And the sine of 60 degrees is root 3 over 2. Okay, so, multiply, and you'll get root 2 over 4 plus root 6 over 4. Common denominator is cute, so you can put them all over, 1, 4, root 2 plus root 6 over 4. Now, this is what I would call a good enough representation of the final answer. But I checked the back of the book because I always want to, know that I'm doing this correctly. And this is how they presented their final answer. They pulled this factor of 4 out as a 1/4 multiplier and put the root 6 first and the root 2 second in the sum. That's not intuitive for me personally, but this is what the back of the book has. So I'll go ahead and formally say that that's the best representation of the final answer, but I find this previous step to be an equivalent way to do it. I'd be curious to see what Pearson says, because sometimes Pearson has pretty strict syntax rules that I'm not always aware of with the homework. So, if you find these to be popping out for you from time to time, feel free to share that with me / the class. I know you guys are in some Snapchat groups or some other kind of groups with one another. Definitely let each other know when you come across nuanced syntax rules associated with the Pearson homework in entering your final answers. Okay, so, but that's what the back of the book wants to see. Cool, cool, cool. Next one. All right. Negative 5 pi over 12. I don't know that one. What's a good way to come up with 5 pi over 12? Well, before we get too deep into that, let's just rewrite the cotangent in terms of cosines and sines, because I think that'll be a really good first move, okay? Okay, so that'll equal the cosine of negative 5 pi over 12 over the sine of negative 5 pi over 12. Okay, cool, cool, cool. Let's use the evenness of the cosine and the oddness of the sine to pull out that negative sign. So that means that the cosine will just not have a negative sign in front of it anymore, or in front of the argument. And then the negative sign in the argument will be pulled out in front of the sine because of the odd nature of the sine function. Okay, here's where I think it would behoove us to do either a sum or a difference that gives us our 5 pi over 12. So I thought about this and I said, all right, what radian measures will give me a difference of 5 pi over 12? And so I thought about, well, I looked at unit circle and I said to myself, okay, well, I need to probably come up with a combination of radians that have denominators of 4 and 3, because that 4 and 3 multiply to 12, right? So I discovered through a little bit of a sidebar, so I'll just do my sidebar in blue, that it turns out that if I take a upload failed. Ooh. Oh, hey, whoa, I didn't do anything. Stop that. Sign in. Whoa, okay, I don't know what that was. Disregard. It looks like, oh, yeah, everything's back to normal. Yikes, I don't know what that was. I think I held my finger down too long. What the hell? Come on. Sign in. Hold on. Let me pause the video real quick and see if I can fix this. Sorry, guys. Okay, weird. I don't know what the hell happened, but I got signed out of my Microsoft Office account and it wouldn't let me use my eraser and stylus. Okay, whatever. Let me just get back to my sidebar. Sidebar. Okay, so I discovered that through some trial and error that if I took 3 pi over 4 and subtracted pi over 3 from it, I would get 5 pi over 12. Now watch this. The equivalent building up to make common denominators with those two aforementioned angles was 9 pi over 12 minus 4 pi over 12. Okay, now these are actually, if you reduce them, 3 pi over 4, right? Minus pi over 3. So this is what we're going to use right here. But I just want to show you that this is gives you a 5 pi over 12 result. Okay, cool. Now how would you get that? Like I said, looking at unit circle very carefully, trial and error, find some angles whose either sum or difference is in this case, we whittled it down to a positive 5 pi over 12. Okay, so now that we know what we're doing here, I'm going to rewrite this as cosine of 3 pi over 4 minus pi over 3 over a negative sine of 3 pi over 4 minus pi over 3. So we're going to use our difference formulas, and it's going to get quite messy here, but it's nothing we can't handle. Okay, so I'm going to go ahead and just continue it over here so I give myself plenty of room, and it becomes the cosine, because if it's a cosine difference, it's cosine, cosine, sine, sine, and you switch the signage, right? So that'll be cosine 3 pi, it's supposed to be a 3, pi over 4, cosine pi over 3, plus the sine of 3 pi over 4 sine pi over 3 over negative. We gotta make sure that negative sign stays outside of the whole situation there. And then the sign is gonna be sine, cosine, cosine, sine, and we, keep the sign, S-I-G-N, inside. So that'll be sine, cosine, cosine, sine, okay, and just checking my notes, make sure I got that all written down correctly. Okay, yes. And so now we're ready to replace all of these cosines and sines with their outputs. So you'll get negative 2 over root 2 over 2 for the cosine of 3 pi over 4, and then multiply that by 1/2 because that's the cosine of pi over 3, plus pi over 2 over 2 times root 3 over 2 all over, and keep that negative sign out in front. We got to deal with that, but we'll wait for a subsequent step. 2 over 2 times 1/2 plus, minus a negative root 2 over 2 times root 3 over 2. Okay, so then these two signs are going to cancel each other out, right? So I could do that in another color just to make sure I show you that it happens, but then we need to distribute through this sign as well, here and here. So it's like, yes, it cancels out, but it becomes subtraction yet again. So fun. Okay, And so then let's go ahead and have this go over here in the next step, and we will go ahead and condense this all down a bit, and we're going to get in the numerator negative root 2 over 4 plus root 6 over 4. That looks familiar, doesn't it? Yep. And then in the denominator, it'll be a negative root 2 over 4 minus root 6 over 4. Gosh, almost exactly the same in the numerator and denominator, right? But this little plus sign kind of ruins the whole thing. So we can recognize that there is a common factor of technically root 2 over 4, which we can take back out of this thing if we want to. So sorry, that was a little bit probably jarring to have that put together and then now taken apart again. But that's what my notes say. Sorry, I didn't really account for that. So let's actually call this root 2 over 4 being pulled out, and that'll be a 1, or a negative 1 rather, plus a root 3 stays behind there. And in the denominator, we'll have a negative root 2 over 4 pulled out, and the remaining bits will be 1 plus root 3. Okay, sorry, that should be a parenthesis. Let me erase that and make it look a little nicer. Okay, so then at least these will be canceled out. And so let me do that, but in red. Boop. Oh, did that not change to red? Goodness. And then go back to that. Boop, boop. It's still negative out here, so let's keep that in mind. And then what did I do? Oh man, what a mess. We still have some more work to do here. That becomes, we want to multiply by the complex conjugate. So, or not complex conjugate, the radical conjugate. So that'll be giving us negative 1 plus root 3 down below. Negative out in front. 1 plus root 3. So we'll multiply by 1 minus root 3. 1 minus over 1 minus root 3. A fun one, okay? So then we'll FOIL up here, and we will get ultimately it'll become 1 minus 3 down here, which will be a negative 2. And it'll be negative, if we have the negative absorb, nope, it'll just be still out in front. And then in the numerator, we'll have 4 plus, or negative 4 rather, plus 2 root 3s. And we can let this negative sign just kind of be absorbed in the denominator, right? So it's like this negative and this negative cancel each other out, okay? And so then we just have to deal with the extra factor of 2 that exists. So it'll be negative 4 plus 2 root 3s over 2. And then this 2 factor has got to cancel with this 2 and a 2 from in here, but there would be still a 2 left over. And then we'll have our final answer, finally, yikes, so much work, of negative 2 plus root 3. And yep, that's the way the back of the book has it as well. Wow, so much work to get to that. And some of these that I've yet to present are also a lot of work. So just get comfortable and feel free to pause here and there after each problem if you need to, just to get some rest, because wow, some of them are quite involved. Okay, whew. So I just want to fully own up to the fact that from this step to this step, there was a lot of algebraic magic that didn't get put down, just in the interest of saving space. If anybody wants to see those steps in class, I'd be happy to demonstrate. But just in the interest of time, for the purposes of this video, I do want to move on to this sine, cosine problem with the 20 degrees and 80 degrees. So this one, we're kind of using the sine difference formula backwards. So what we see is the result of, this is using the formula for the sine of 20 degrees minus 80 degrees, believe it or not, because we have a sine, cosine, cosine, sine with a subtraction. So that means the first degree measurement given minus the second degree measurement given inside of a single sine is equivalent. So what does that look like? Well, this is it. Here, this is the sine of 20 degrees minus 80 degrees. And what's 20 degrees minus 80 degrees? Well, it's negative 60 degrees. Can we have negative degrees? Well, of course we can. And because the cosine is an odd function, we could take that, negative sign and just kind of bring it out to the front. And we know what the sine of 60 degrees is, right? It is root 3 over 2. But wait, don't forget, it's negative. So slap that negative sign down in front, and you're done with this one. That one was relatively quick and easy. Oops. Bing, bang, boom. All right, for this next example, we have yet again another tangent, or another backwards use of the formulas, where this is exhibiting, believe it or not, the tangent of the difference between the 40 degrees and 10 degrees. So we can equivalently write this one as tangent of 40 degrees minus 10 degrees. So much easier to go the reverse direction, huh? And that's tangent 30 degrees. Which you may or may not know. If it helps you to break it down into sines and cosines, personally I like to do it this way, where I'm like, this is the sine of 30 degrees over the cosine of 30 degrees. And then that gives me 1/2 over root 3 over 2. And then I slash those 2's away, and then it's 1 over root 3, which is root 3 over 3, rationalizing that denominator. Okay, done skis on that one. And it's nice that we have a couple of these problems that are real quick and easy, because this next one is a doozy. I mean, this next one, number 40, is a 4-parter, so you know, it's legit a lot of work. And especially when we get to this tangent, I do not know why that tangent is capitalized. Let me just go ahead and edit that real quick. Should not be capitalized, no reason for that. But yeah, we're going to establish the sums of sine and cosine, the difference of sine, and the tangent difference identities for the following scenario, in which the cosine of alpha is 1/2 and alpha is somewhere between negative pi over 2 and 0. So that is to tell us something about what we should expect the sign to, this SIGN of the SINE, the sine's sign should be negative for alpha, just heads up. And then the sine of beta is 1/3, and then beta is somewhere between 0 and pi over 2. So that means that the cosine will be positive. And so the first thing that we'll want to do here, because we're going to get the sums, differences going on for these sines and cosines. So we need to figure out what the the sine of alpha and the cosine of beta is. And the way that we'll do that is to use the Pythagorean identity of sine squared beta. Oh, well, let's do beta first for no particular reason. So we've got sine squared beta plus cosine squared beta equals 1. We know this, right? That's the Pythagorean identity. Well, you know, go ahead and put sine beta in and square it for this first term. We'll get 1/3 squared. And we'll be able to solve for cosine beta in a couple of steps. So that'll be 1/9. Oops, that's supposed to be a 9. Sine squared beta equals 1. Call that 9 over 9. So that way cosine squared beta equals 8/9. And so therefore cosine beta equals 2 root 2 over 3. And again, because beta was between 0 and pi over 2, we're definitely taking the principal square root here and not the negative one. Okay, so let's go ahead and similarly solve for cosine or sine alpha rather. So sine squared alpha plus cosine squared alpha equals 1, duh. Instead of cosine alpha, let's put in 1/2. Yeah, sorry. Checking my notes there. We're good. And square it. And we'll be able to eventually solve for sine alpha. So sine squared alpha plus 1/4 equals 1. And then let that one be a 4 over 4, right? So subtracting this from both sides, we'll get sine squared alpha equals 3/4. And therefore sine alpha will equal negative root 3 over 2. Hopefully everyone can follow that just fine, recognizing that it was established that alpha had to be between negative pi over 2 and 0. So that means that we should expect our sign to be negative, okay? Because the angle inside whatever alpha is, it's supposed to be negative, and so we know that sine is an odd function, so the negative sign will be associated with the resulting value there. Okay, so we have cosine beta, cosine alpha, and sine alpha, and we were given sine beta and cosine alpha. So now we have everything we need to do these sum and difference expressions. Okay, so let's start with part A, sine alpha plus beta. So we could do the chant, sine, cosine, cosine, sine, and sine, cosine, cosine, sine. Sorry. Which equals negative root 3 over 2 times 2 root 2 over 3. And now it's just an algebra game, plus 1/2 times 1/3, which equals negative 2, sorry. Oh, did I meant to put that's a 2 right there. My bad. I put a 3 inside of that second radical, and I really meant a 2. It's 2 root 2 over 3. So that's a negative 2 root 6 over 6 plus 1/6. So you can put it all on 1. And also they switch the positions of these two. So the final answer according to the back of the book is 1 minus 2 root 6 over 6. Okay, cool. So just a little bit of algebraic manipulation that may or may not be intuitive to get the final answer in the way that the Pearson textbook authors like. Okay, so there we go. Let's do the cosine addition of the two angles alpha and beta, and that'll be cosine, cosine, sine, 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 where you know that first sign that's mentioned as SIGN, where we're going to change the sign from addition that's going on inside of the argument to subtraction in the resulting formula value. So that'll be cosine, cosine, sine, sine, sine. So hopefully those are helpful. And then that'll give you a value of 1/2 times 2 root 2 over 3 minus negative root 3 over 2 times 1/3. Oh, and before we go any further, I just want to fully recognize that at least for this one over here. You might have not needed to do the Pythagorean identity to get this negative root 3 over 2. I mean, that's, you know, 1/2 being the cosine of alpha is a relatively, you know, benign and familiar output. It's just like if you wanted a mechanism to be sure that you're going to calculate it correctly, you can always use the Pythagorean identity. Okay, so for some of you, this latter calculation might have been unnecessary. Okay, but moving back on to what we were doing here, let's just go ahead and simplify this out, and we should get, well, oh, some things cancel here. These 2's cancel, so let's go ahead and establish that. Boom, boom. And then we get root 2 over 3 for that first term. And then minus, because, oh, those signs kind of cancel each other out. So that'll be plus root 3 over 6, right? Yep. In the textbook, authors are like, hey, let's have common denominators here. So they multiply this first term by a 2 over 2, and they get, and then they switch the positions of these two for some reason. Root 3 plus 2 root 2 all over 6 is their final answer. So again, if you want to see some more algebraic details on that, just let me know and we can talk about it in class. All right, so the sign is going to be sine, cosine, cosine, sine. Sine, cosine, cosine, sine, which equals negative root 3 over 2 times 2 root 2 over 3 minus 1/2 times 1/3, which equals negative 2 root 6 over 6 minus 1/6. So make it all in under, you know, over one particular 6 and change the positions of the numerator values for whatever reason. That seems to be the convention, and that'll give you your final answer here. All right, now for the tangent difference, we have to do some more work because we want to know what the tangent alpha, tangent beta is. Because, so one thing we could do right away is say, all right, well, what does this equal? The tangent is, for the difference, is you're going to maintain the difference of the tangents in the numerator. So that's tan alpha minus tan beta over 1 plus, yeah, switch the sign, tan, tan, done. Remember that cute song that one woman had in the video? So there we go. So that's the formula, but you may be wondering, oh crap, what's tangent alpha, tangent beta? It'd be cool if I did a little bit of sidebar work on that. So let me change the color. We'll do a darker blue, and we'll do a little sidebar. So tangent alpha is sine theta, hold on, or sine alpha rather, over cosine alpha, which is what? Root 3 over 2, negative root 3 over 2 that is, over 1/2. And this one you might be able to do even quicker than what I'm doing. And those cancel, and it's just negative root 3, right? Cool, you knew that. Negative root 3. Great. Now for tangent beta, that's sine beta over cosine beta. Duh, we get that. Equals 1/3 over 2 root 2 over 3. Let's do a little slashy slash on that with the 3's. Cute. And then we will have 1 over 2 root 2. but we need to, you know, rationalize the denominator, so it'll become root 2 over 4. Hopefully everyone's okay and on board with that. Okay, so we have our sine alpha and sine beta. Let's go ahead and plug those things in to our tangent formula here and go to town. All right, so that'll be equal to, nope, I want it black. Tan alpha is negative root 3 minus root 2 over 4. It's supposed to be a negative, and then that's over 1 plus root 3, negative root 3, times root 2 over 4. Okay, now simplifying this down is like kind of an endeavor, so buckle your seatbelts, folks. We're gonna go in this direction first, and then let's see, we have a little bit of room down below to continue, so we're going to snake around as far as our steps are concerned. Now the first thing that we're going to want to do is both the numerator and denominator get common denominators going in each of those individual spaces. So for the supernumerator, we should get negative root 3, 4 of them rather, and then we'll subtract off a root 2, and that'll all be over a 4. So this is making a common denominator happen for the first term of by multiplying by a 4 over 4. Okay, so that's the supernumerator. And then the denominator, let's go ahead and make this a 4 over 4, this 1, and then we'll be able to add it to, well, subtract really. This, it ends up being a root 6 over 4, right? So we'll have 4 minus root 6 over 4 there. What's kind of cool about this is that those 4 denominators within the supernumerator and superdenominator can actually cancel out, but then you're left with a radical a binomial down below that you're going to need to multiply by its conjugate. Nothing we can't handle though. Let's just, actually, I want to erase this and make it not so long because I need all the room I can get. Okay, so then here this becomes negative 4 root 3 minus root 2 over 4 minus root 6. Okay, so what I mean by multiplying by the radical conjugate, I mean multiply by a 4 plus root 6 over a 4 plus root 6. Okay, and you're going to use the sum difference product rule in the denominator to go straight to this being 16 minus 6. And in the numerator, you're going to FOIL this out. And initially, it's going to be this mess of negative 16 root 3 minus 4 root 18. Don't worry, we're going to simplify these radicals in a subsequent step. Minus 4 root 2 minus root 12. Let's see if I can fit all this in. Yikes, just barely. Okay, so this is going to be equal to something that I'm going to put all the way over here. So fun. Okay, negative 16 root 3. Let's simplify the radical stuff. So this root 18 simplifies to 3 root 2's, but the 3 multiplies to the 4 that's out in front, so it becomes a minus 12 root 2. And then we're going to subtract off the 4 root 2, which can't be simplified any further, but the root 12 certainly can, and that'll become a minus, 2 root 3. So, and then the 16 minus 6, call that a 10. Oops, a 10, not a 16, 10. Okay. So now combine the root 2's and the root 3's, and you'll have minus 18 root 3's minus 16 root 2's. Over 10. The 10, the 16, and the 18, they all share a factor of 2 that can be slashed out. So if you slash out a factor of 2, you're left with 5 here, 8 there, 9 there. And then your final answer, therefore, switching these two terms for seemingly no apparent reason, you get negative 8 root 2's minus 9 root 3's all over 5. Wow. And that's your final answer. Oh, Lord. Feel free to press pause and take a break from that, because that is just wild. Okay, I have two last examples, and they're not nearly as crazy. We're going to establish the identity, so we're going to go back to that whole chart kind of format, and it's not nearly as crazy as a lot of those other ones have been, okay? So here we go. Let's go ahead and, oh, you know what? I'm going to decide that I need more room than what I'm giving myself here. So I'm going to put the vertical bar over here and say this is where the equal sign should line up. Okay, so then what am I going to do? I'm going to use the tangent difference formula, which is tan 2 pi minus the tangent of theta over 1 plus tangent 2 pi tangent theta. Okay, now tangent of 2 pi, that's something that we can calculate, okay? So the tangent of 2 pi is the same as the sine of 2 pi over the cosine of 2 pi. What's the sine of 2 pi? Does anybody know? Well, it's 0. So if the sine of 2 pi is 0, the tangent of 2 pi is 0. So this right here zeroes out. That's a 0. And this whole term, therefore, is a 0. Because this zeroed out, right? So this is 0, so the whole darn thing is gone, all right? So we can establish this at this point and say, all right, now we're just left with what? Negative tangent theta over 1. Well, that's just negative tangent theta. And look, that was what I was trying to establish, so I am done here, folks. See, quick and easy on that one. Whew, such a relief to have something so straightforward after that. Number 40 was just a monster. All right, one more and then we are absolutely done with this lecture video. And this one is quite involved. Okay, so we're going to try and establish this difference of cosine squared alpha, that is, and sine squared beta based on these difference expressions on the other side here. So I'm going to go ahead and use the formula. Now we're talking cosine, so it's cosine, cosine, sine, 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 in which we change the signs and all that stuff. So this first one is going to be cosine, cosine, sine, sine, sine. And that's going to be multiplied by this other version of cosine, cosine, sine, 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 but the sign will be changing into subtraction, so that'll be cosine, cosine, sine, sine, sine. Okay, and then what I'll do here is I will recognize that I have some difference product rule that I can implement to relatively quickly call it the following: cosine squared alpha, cosine squared beta, minus sine squared alpha, sine squared beta. Now you're going to do a little bit of algebraic trickery, which is what I would deem totally non-intuitive, okay? You're going to want to take this sine squared beta right here and use the Pythagorean identity to recategorize it. So we'll call it cosine squared alpha. Instead of sine squared beta, we'll call it 1 minus sine squared beta. How would you know to do that? Probably wouldn't, but that's why I'm showing this to you. Okay, then go ahead and distribute this through, this cosine squared alpha. I know, seems weird, but just stay with me here, folks. It's going to turn out to be just glorious in just a moment. Sine squared alpha minus cosine squared alpha, sine squared beta, minus sine squared alpha, sine squared beta. Now you'll want to use the fact that these last two terms have a common factor of sine squared beta, and go ahead and not only sine squared beta but also a negative sign. So go ahead and pull both of those items out and it'll look like this: cosine squared alpha minus the sine squared beta that they share. And what's left? Cosine squared alpha plus sine squared alpha. Isn't that tasty right here? Because what is the value of cosine squared alpha plus sine squared alpha? Well, your Pythagorean identity says that its value is 1. So that just becomes a factor of 1. And then we are left with just cosine squared alpha minus sine squared beta as desired. So sometimes you will have to do some really just intensely creative algebraic trickery there in order to get through some of these, but that'll be a fun exercise for your brain. So good luck, and make sure that if there are any questions that you have along the way while watching this, well, hopefully you've been writing them down in the margins, and let me know if there's any particularly algebra that's been skipped over that you'd like to see in more detail, or if you'd like to see more examples of these types, just fresh ones, like I love to demonstrate in class, just let me know. Okay, thanks for your attention, guys. Bye.